Hello there, this is Jude Socrates. Welcome to today's video on infinite series. And today we are going to talk about the divergence test, which is also known in some books as the test for divergence. We're going to cover section 2C from my textbook. And if you still don't have a copy, kindly go to the description of this video. You will see a link to Dropbox and you can download my book there. I hope you enjoy it. So before we see the statement of the divergence test, we're going to have a little bit of a warm-up. We're going to talk about basic logic. Okay, so if you're in college, you might have taken a course like Philosophy 101 or something like that. And we're going to talk specifically about implications. So an implication is simply a sentence which is of the form, if condition X is true, then condition Y is also true. So X in this sentence is called the hypothesis of the implication, and Y is called the conclusion of the implication. Not all implications are true. Some are true, some are false. So the implication says, if condition X is true, then condition Y is also true, which means that anytime condition X is true, it should also follow that condition Y is true. If there is ever an example where condition X is true, but condition Y is false, then we know that that implication is false. So such an example is called a counterexample, where we see that the implication fails for that example. All right, so let's start with this implication, something easy, okay? If you live in Los Angeles, then you live in California. That is an implication. The hypothesis is you live in Los Angeles. The conclusion is you live in California. All right, well, this is obviously true because if you live in Los Angeles is inside California. So it is also true that you live in California. Okay, we are going to manipulate implications in the actual test for divergence. So let me tell you that there are three ways by which we can manipulate an implication. So the first way is to create its converse. In the converse, you simply exchange the conclusion with the hypothesis. All right? So we will get, if you live in California, then you live in Los Angeles. In other words, everyone who lives in California lives in Los Angeles. Obviously false. You can live in San Diego, you can live in San Francisco, Bakersfield, anywhere but Los Angeles, and still live in California. Okay? So every person who lives in Bakersfield serves as a counterexample to this converse. Okay, so this converse is obviously false. Okay, so by the way, let's label this. This implication is obviously true. Okay, I'm not giving you a very difficult example. I want everyone to understand this. Okay, so what we're going to do in the divergence test is to construct what's called the contrapositive. Okay? The contrapositive is take the converse but negate both the hypothesis and the conclusion. In other words, the word not or don't or never will appear in both of these phrases. Okay? So in this example, the easiest, most natural way to write the contrapositive would be, if you don't live in California, then you don't live in Los Angeles. Okay? So you live anywhere in the world except California. So maybe you live in Nevada or New York or Europe or Asia or South America. In which case, it's impossible for you to live in Los Angeles because Los Angeles is inside California. Okay, so we started out with a true implication. This is the contrapositive of the original implication. And this implication is also true. Okay, so it turns out that an implication and its contrapositive are what's called logically equivalent. Okay, so in math, we talk about equivalent formulas or statements. In this case, it means that an implication and its contrapositive are either both true or both false. If one of them is true, then the other is also true. Okay, so this idea is what we are going to use in order to understand the test for divergence. I said that there are three ways to manipulate an implication. The third way is to create what's called the negation of the statement. Okay, so the negation would be go to the original implication, this one, and then you negate both the hypothesis and conclusion. Okay, so it would say if you don't live in Los Angeles, then you don't live in California. So again, that's false. If you don't live in Los Angeles, maybe you live in San Diego. Well, you still live in California. Okay, so you satisfy the hypothesis of not living in Los Angeles, but you don't satisfy the conclusion of not living in California. Okay, so in the same way that an implication and its contrapositive are either both true or both false, the converse and the inverse of an implication are also logically equivalent. I didn't even bother to write that down because what we are going to be interested in is the contrapositive version of the test for divergence. Okay, we're ready to go now. I'm going to take you to our textbook. All right, so this is what the divergence test says. Suppose that summation n equals k to infinity of a sub n is an infinite series such that the sequence of terms, the sequence a sub n, n from k to infinity, which make up the series, if the sequence does not converge to zero, then the infinite series automatically diverges, or it diverges to infinity, or to negative infinity. So, in other words, the series automatically does not converge. All right, so one more time. You start with an infinite series. You look at the terms of that series, not the partial sums. We talked about the partial sums last time, but all you have to do is look at the terms that make up the infinite series. If those terms do not converge to a limit of 0, maybe they converge to 7 or negative 4, or maybe they diverge to infinity. Those are all included under the condition does not converge to 0. Anything but 0. Then we can automatically say that the infinite series diverges, or diverges to infinity, or to negative infinity. Sometimes it's possible to decide which of these three divergences will happen. Okay, so let's go over the proof, and as I said, it has to do with the contrapositive of this statement. Okay, so we covered this a few minutes ago. The implication is if something is true, then something else is true. One example, one very good example that we see in calculus has to do with differentiability and continuity. If a function is differentiable on an interval I, then the same function is also continuous on I. All right? So we know that this statement is true if you've taken basic calculus, and of course you have because you're in second semester calculus. A function which is differentiable is also continuous. So this is the contrapositive, but before we get there, let's think about the converse of this statement. If a function is continuous on an interval, can we also conclude that the function is differentiable on that interval. In other words, it's enough for a function to be continuous so that it's differentiable. True or false? Well, I hope you remember a famous example of a function which is continuous, but there's a point, just one point, on that function where it's not differentiable. The derivative does not exist. You remember what it is? It's the absolute value function. Okay, so it has a corner, and at that corner, your function fails to be differentiable. All right, so the converse of this statement is false. The implication is true, but not its converse. Okay, however, the contrapositive is also true. Remember that an implication and its contrapositive are equivalent. So if one of them is true, the other is also true. If a function is not continuous on an interval I, then the function is also not differentiable on I. If there's at least one point of discontinuity, then the function fails to be differentiable at that point of discontinuity. Of course, we know that this is true. If it were differentiable at that point, it would also be continuous because the original implication is true. All right, so there we go. The absolute value function is a counterexample of the converse, so it's not a true statement. So remember, to write the contrapositive of an implication, you exchange the hypothesis and the conclusion. So the conclusion now becomes the first part of the sentence, and the hypothesis becomes the second part of the sentence, but you get the negative of both the conclusion and the hypothesis in their new positions. Okay? So in other words, we will have, if the conclusion is false, then the hypothesis is also false. So that is the equivalent statement for the contrapositive. Okay, so what did the divergence test say? If the terms do not go to zero, then the series diverges. Okay, so the conclusion is the series diverges. The opposite of that conclusion would be to converge. What is the opposite of does not converge to zero? Well, it will have to be converges to zero. So now we are able to write the contrapositive of the divergence test, which says, if a series is convergent, then the terms of that series must converge to zero. All right? If a series, summation n equals k to infinity of a sub n, is a convergent series, then the terms of that series must converge to zero. This is a lot easier to prove than the original divergence test, and that is because now we can talk about the sequence of partial sums. All right, so remember that if your series starts at ak, then sk is just ak. Sk plus 1 is sk plus ak plus 1. In other words, every partial sum is the last partial sum where now we add the current term of the infinite series. All right, so in general, we can say that Sn plus 1 is the last partial sum, Sn, plus the next term, which is a sub n plus 1. And we know that these partial sums converge to some limit s because we are told that your series is a convergent infinite series. So remember that that means that the partial sums must converge to some limit s. All right, so now we simply solve for a sub n plus 1. A sub n plus 1 is simply s sub n plus 1 minus s sub n. All right, but since the limit of s sub n is s, then the limit of Sn plus 1 is also s, right? Because it's just the next term in the series, the sequence of partial sums. So if your partial sum is already within epsilon, of your limit, then everything beyond it will be also within epsilon of that limit. So that next term will also converge to the limit s. All right, so now we simply take the limit of a sub n using properties of limits. The limit of a sub n plus 1 is the limit of Sn plus 1 minus Sn, which we can break up into two limits. And we said that both of these limits are s, and therefore the limit of the difference is simply 0. Okay, so therefore limit of an plus 1 is 0, so backing up, limit of a sub n must also be 0. All right, so we're going to look at several examples, more than just 3, because we are going to build, sorry about that, we're going to build on what we see in the screen right now. All right, so here is our first example, and maybe I shall, let's see, let's label them. Okay, so this will be our example A. Summation n equals 1 to infinity of 5n plus 7 over 3n minus 2. Right? So our a sub n for the series is 5n plus 7 over 3n minus 2. Okay, so you did your homework in part 1. We saw sequences like this, and we know that since the degrees are the same in the numerator and the denominator, then the terms simply converge to 5 over 3, coefficient of the highest term in the numerator and the highest term in the denominator. All right, so that is, limit is 5/3, which is not 0. Okay, so according to the divergence test, okay, so this satisfies the hypothesis of the divergence test. So the dp applies. We can conclude that this series diverges. Okay, so can we be more particular that this diverges to infinity or minus infinity, or it just goes back and forth, crazy? Well, the terms get closer and closer to 5/3, so the terms are positive. Maybe A1, oh yeah, A1 is already positive, A2 is positive, and so on. So we're adding up positive terms that don't go to 0, but they approach 5/3. So it's almost like we're adding, after a while, terms which are approximately 5/3 to the partial sum. Okay, so since 5/3 is positive, we can conclude that this series diverges to positive infinity. Okay, so for this example, the divergence test does apply. Okay, we are going to create a second example from this. So let's change this to example B. Okay, so this time, let us turn this into an n squared. Okay, 3n squared minus 2 in the denominator. Okay, so our a sub n is now 5n plus 7 over 3n squared minus 2. So this time, the degree in the numerator is n, but in the denominator it is n squared. Okay, so it's not very obvious what that limit should be. Maybe it's obvious to you, but let's make sure everyone sees it. Okay, so same technique as we have in basic calculus. Multiply and divide by the highest power. But yeah, the highest power in the numerator is not the same as in the denominator. Let's try 1 over n. Okay, so we will get the 5n simply becomes 5, and the 7 becomes 7 over n. The 3n squared gets cut down to 3n, and minus 2 over n. Okay, so let's analyze what's happening here. 7 over n, that limit is 0, minus 2 over n, that limit is also 0. So these two terms are getting very, very small, close to 0. Which means that the numerator is approaching 5. Okay, so that makes sense because in our last example, the numerator goes to 5. But the denominator is 3n minus something that goes to 0. Okay, but n is getting bigger and bigger, n is going to infinity. So if n were like 1,000, you will get 3,000 minus something really small, it's less than a penny, something really small here, and 5 survives in the numerator. So you get something which is close to 5 over 3,000. Okay, well that's a very small number. Okay, so that limit is going to be 0. Okay, so do we satisfy the hypothesis of the divergence test? No. The test requires that the terms do not converge to 0. Since the terms converge to 0, the divergence test does not apply. Okay? We cannot form any conclusions about this series. It may converge or it may diverge. Okay? So actually, in a couple of videos, we will find out that this series, in fact, diverges. Okay. So yeah, it may or may not converge. In this case, it diverges. All right. We are going to go back to our original series. And this time, part C. This time, we are going to change the numerator. Okay? So instead of 5n, this time, we'll put the square in the numerator. All right? So our a sub n is going to be 5n squared plus 7 over 3n minus 2. Okay? So, yeah, before, in part B, we did multiply and divide by 1 over n. Is that going to work again this time? Okay? So, we're going to see this time, n squared becomes just n. 7 will become 7 over n. 3n this time becomes 3. And minus 2 becomes minus 2 over n. Okay, so once again, what's happening in this fraction? 7 over n and 2 over n are both getting very, very small, close to 0, which means that the denominator is approaching 3. But the numerator has this 5n. So again, if n is like 1,000, then you'll get 5,000 plus a little bit more. Oh, good, I have a few pennies there. But we're dividing by 3 and something close to 0. Oh, practically 3. 5,000 over 3, still way over 1,000. So it looks like these terms are getting bigger and bigger, right? So I hope that you agree that the limit of the sequence is now positive infinity. Okay, so do we satisfy the hypothesis of the divergence test? It says that your sequence does not have 0 for a limit. Well, infinity is not 0. Since the limit of the terms is infinity and not 0, then we satisfy the hypothesis of the divergence test. Okay, so thus we can conclude that this series diverges. And will it be diverges period or diverges to infinity or minus infinity? Well, once again, we're going to get oh, the original will have 1,000 squared here. It will get 3,000 here though. But the point is that the terms are getting bigger and bigger, approaching infinity. So that the series diverges, and since the terms approach infinity, the series diverges to positive infinity. Okay, so we are allowed to make that conclusion. All right, so we have these two other examples, and we're going to build on this in a minute. This is now part D. Yes, part D. We have this, and I hope you recognize that this is a geometric series. In fact, it's from one of our earlier videos, the second video. Okay, so this is a geometric series, and the common ratio is -3/5. And we said that a geometric series converges if and only if the common ratio is between -1 and 1. Well, this is between -1 and 1. This is a geometric series with r equals -3/5. So by our theorem on geometric series, this series converges. And in fact, we have this formula, the sum is 1 over 1 minus r. Okay? And this exact same series was in that video. All right. However, our a sub n is -3/5 to the power n. And in part 1, we looked at geometric sequences. And we said that if r is between -1 and 1, then r to the n will converge to 0. Okay? So, do we satisfy the condition, the hypothesis for the test of divergence? No, we don't. The sequence, the geometric series, converges to 0. Since a sub n converges to 0, we do not satisfy the hypothesis of the divergence test. Okay? Which doesn't mean that this series diverges or converges according to the divergence test. It simply means we cannot make any conclusion based on the divergence test. We can still make a conclusion based on what we know about the geometric series. Okay? We still conclude that this series converges, but due to our theorem on geometric series. Okay? The divergence theorem does not allow us to make a conclusion about this series. Okay? We need something else, something stronger, namely our theorem on geometric series. Okay? So in other words, something could be true based on a line of reasoning, but not on a different line of reasoning. In other words, we know something about this series because we have seen it before. We have a new tool now, the divergence test, but we cannot use it on this series because the terms go to 0. We do know what it does because we know a little something about geometric series. Okay, so what if we now change this example? This is now part E, and instead of -3/5, we have -5/3. Let's flip the fraction. So this r is now less than -1. Okay, so we have to go back to part 1, where we saw geometric sequences. And we said, okay, if you square, you get something positive. If you cube, you get something negative. So yeah, you want to review that? Let's do that. What happens if we take the terms and we square, we cube, we take to the power 4, we take to the power 5. Okay, what's happening to the terms of the sequence? Okay, we get 2.777 cubed, negative 4 point something, fourth power, we get, all right, let's try that again, 7.71, fifth power, we get negative 12.86. All right, are we approaching 0? Clearly not, right? So I hope you remember from part 1 that in this case, the terms diverge. They don't diverge to infinity, they don't diverge to negative infinity, because you can get big positive numbers, but also big negative numbers. Okay, so you're not approaching plus infinity or minus infinity. Okay, do we satisfy the hypothesis of the divergence theorem? Our sequence does not go to 0. Thus, since our terms diverge and do not go to 0, we satisfy the hypothesis of the divergence test. Okay, thus we can conclude that by the divergence test, this geometric series diverges. Okay, so whereas in the last example, when the geometric series converges, the divergence test does not apply. In this example, the geometric sequence diverges, so the test for divergence does apply. But we already knew, once again, we already knew in part 2b, section 2b, that when the common ratio of a geometric sequence, of a geometric series, is not between -1 and +1, forget it, your series diverges. In this case, it doesn't diverge to infinity or negative infinity. It simply diverges because you get big positive numbers and big negative numbers. So this is the worst kind of series where it simply diverges. Okay, so last one. This was the telescoping series that we saw in our last video as well. So we are now in part F, last example. Okay, so this is a telescoping series, and we know from that video that we were actually able to find the exact sum of this telescoping series. We were able to find the exact sum of this telescoping series. Okay? In other words, it converges. Okay, but back to the topic. Does the series satisfy the condition, the hypothesis of the divergence test? Our terms, A sub n, are this. 5n plus 4 over n plus 1, n plus 2. Okay. Simple, linear. Okay, but this one, n, we have an n cubed. Okay, which is worse than n squared. So, using the same trick that we did earlier, multiply and divide by 1 over n, check it out. If you divide by multiply by 1 over n, that n goes away. We're just left with n plus 1, n plus 2 in the denominator. So as n gets bigger and bigger, this denominator still gets bigger and bigger without bound. And the numerator will only have 5 plus 4 over n, about $5. Ooh, okay. So the numerator is stuck at around 5. Denominator is getting bigger and bigger and bigger. We're dividing by a huge number, so therefore that limit is 0. All right. Do we satisfy the hypothesis of the divergence test? No, we don't. The limit is 0. Since the limit of the terms of the series is 0, the divergence test does not apply. We cannot use the divergence test to conclude that this series diverges, let alone converges. Okay, so before I end this video, let me tell you in no uncertain terms. The test for divergence cannot be used to conclude that a series converges. Look at the name. It says test for divergence. The only conclusion that we are allowed to draw by applying the divergence test is that the series diverges. We can never make the conclusion that the series converges. You don't believe me? Let's go back to the first example. The terms here do not go to 0, so we can conclude that the series diverges. The terms here do go to 0. The test does not apply. We cannot form any conclusions. It may converge, it may diverge. We're going to see something else in a couple of videos that will allow us to make a decision. This one, the terms go to infinity. We can conclude that the series diverges, and in fact diverges to positive infinity. Geometric series. We use the theorem on geometric series to conclude that this series does converge, not the divergence test. The divergence theorem does not allow us to make a conclusion about the series. We know about it using something else, but not the divergence test. Other geometric series, but this time the terms go diverge, not to infinity or negative infinity, simply diverge, so we can conclude that the series diverges. So last example, we don't know if this series converges or diverges because the terms go to 0. The divergence test does not apply. Okay, so I cannot emphasize this enough. You should never conclude that a series converges based on the divergence theorem. You can only conclude that the series diverges if the condition holds that the terms do not go to 0. If they go to 0, like this one, there is no possible conclusion. All right, so that is our video for today. I hope you found it useful. So next time we are going to continue with the first test for infinite series that will allow us to conclude if a series converges, and also will tell us if it diverges. So this time we will be able to reach one of the conclusions, and not just in this case where the only conclusion we're allowed to draw is that our series diverges. All right, so until then, I hope you enjoy the rest of your day. Bye.